Okay, so the last section to cover in this chapter is on complex ions and then the calculations involving complex ions. I just wanted to point out I'm going to leave some other problems in the slides related to something called sulfide precipitation. It's not really covered in this book, but I don't really want to delete them from my notes, and so I'm just going to leave them in there. But complex ions are formed when you have an ion and it reacts with something called a ligand. And a ligand is a Lewis base. There's a lone pair of electrons that attaches to the metal ion. And that's called a complex. It's not because it's complicated, but because it forms a structure in solution. And that structure is ionic. And so as a result, unlike precipitation where the charges neutralize each other, the charge allows the complex ion to remain in solution. So I'll give you some examples of what complex ions look like and then what their equilibrium constants and expressions look like. Okay, so here's an example of a silver cyanide complex ion. Now, how do you know the formula for this, right? The way you know it is that you look it up. Otherwise, I'm not exactly sure how you would know it, honestly, at this point. Okay, so there are some rules that you learn about the number of ligands, that's the cyanide ions, that will attach to the silver, or the number of these types of ligands that will attach to the iron. But for the most part, at this point, it's just straight look it up. Okay, so we have a formation constant. It's called a Kf, and that is for the formation of the complex ion from its ions. I guess that's the best way to put it. So you have silver ion plus 2 cyanide ions, like this, makes the complex ion Ag Cn2. And then these brackets don't mean molarity now. These are the brackets for the formula for the complex ion. That's how we designate it. So if you really wanted to do a molarity, you would put brackets around the brackets, and that would be the molarity. So Kf then is, again, products over reactants. Because these are ionic compounds, all of these are aqueous. Or ions, I should say. All of them are aqueous. And so at the top you'd have your complex ion, which I'm not going to rewrite. I do this a lot of time in this section because it's just painful to write them all over again, times Ag plus times Cn minus squared, like this. Okay, so that would be how you would do a complex ion. That's for Kf. Now, I should point out that there's also such a thing as a Kd. That 3 doesn't belong there. And so I'm going to write the Kd for this. Kd is just based on the ions you have. Well, that's 2 plus. And these are neutral, actually. But they're still aqueous, like this. And so this is the Kd reaction. And then this is actually just equal to 1 over Kf. Okay, so I'll talk about these. Actually, we talk about these much later in the semester, like how do you know what their formulas are, or what En stands for. This actually stands for ethylene diamine. So that's really a structure that looks like this. Ethylene is CH, like this. And then be the Lewis structure, sorry. And then you have amine groups on the ends like this. So that would be ethylene diamine. And so that's En. It's a neutral, it's an amine, it's a Lewis acid or base because it has lone pairs on it. Cyanide would also be a Lewis base because of the lone pairs of electrons, and what they do is they bind to the d orbitals of the metal ion to form the complex ion. So really a Kf, right, is for the formation. A Kd is for the dissociation, is what that means. And the relationship between Kd and Kf is just, since you're writing the reaction in reverse, it's just 1 over Kf for Kd. So complex ion calculations can be a little bit tricky, and I'm going to work this out on the next slide. But first of all, unlike KSPs, KFs are really large, okay? And so what tends to happen is we would say equilibrium is very far to the right-hand side. And I'll sort of illustrate this with the number line example that I used earlier for KSPs, but in essence, we're working on the other end of the scale. So if you're given reactants, right, just like we did before, you'll go ahead and you'll calculate as if everything went to completion, and then calculate back to equilibrium. So the problem is relatively straightforward. It says, what is the silver ion concentration of a solution that is initially 0.03 molar in silver nitrate and 0.1 molar in sodium cyanide? And basically the steps are the same as the problems that we've done before. You look up Kf, you write the reaction, and then you fill out what you can, basically, in the ice table, and then you work from there, okay? Okay, so using sort of the number line example, what we know is Kf is way over to the right-hand side. So again, this number line is Q. Kf is over here. Then right next to it's infinity. Of course, you know, that's not like really true. And this is 0. And what you're doing when you're setting up a problem in your given concentrations, you're starting over here somewhere. And then as the complex ion forms, you're shifting over to the right. Eventually you reach the Kf point and then it stops. But this is the same problem that we had before. This is your X. And the X is large compared to the numbers that you're starting with in terms of molarities. And so when you subtract X to figure out like how much of an ion is left, you don't get an answer because your calculator will blow up in your face, basically. Okay, so we're going to set up our reaction. Now, here's the thing. Ag and Cn, those are the two ions that are going to form your product. And we know that Ag plus Cn minus is going to make some sort of complex ion, but you need to know what the formula is. Now, I covered this one earlier. Oh, sorry. Here, AgCN, and the equilibrium constant for it was 1 times 10 to the 20th, right? So we know what the formula is. So I know it's AgCN2 with a -1 charge. And just to sort of iterate, right, there's 2 negative charges from the Cn, so 1 positive. So you have an overall -1 charge. And to emphasize this, right, I didn't remember what that was when I was your age. I couldn't, like, just remember all those different formulas. I looked them up, right? They're in the table at the back of your book in Appendix 2 at the very end of all the equilibrium constants. The last one's covered. So I just looked this up. I get the formula, and then I write the ions on the left side. So my Kf for this is 1 point, actually it's just 1 times 10 to the 20th, like that. Now what I'm going to do is this. I'm going to fill in my ice table. And I have molarity units now, so I'll just stick with molarity units. I have 0.030 and 0.10. Now those are my molarities, and again, you have to sort of interpret 1 silver for every silver nitrate, so the concentration of silver is 0.03, and 1 cyanide for every sodium cyanide, so the concentration of cyanide is 0.1. Again, if you're given volumes and molarities, you would have calculated millimoles, because it's easier at that point to work with millimoles often rather than calculating the diluted concentrations. So this is my initial and my change. Now, unlike solubility products, we have to put a 0 there, because that's going to form, it's not a solid, right? So it's going to stay in solution. And then I'm going to have a -x and a -2x. and plus X. And then, oops, sorry, that's the answer. So what I'm going to do then is say which one of these would be the limiting reactant. Now, if I said Cn minus was the limiting reactant, X would be 0.05, and when I subtract that from 0.03, I would get a negative number. So this must be the limiting reactant. So I'm going to set this one to 0, and then the Cn concentration will be 0.0. Let's see, what will it be? 0.4? Like that, yeah. And then over here, I'll have 0.030, like that. Then all I did was took X, I just assumed that X is equal to 0.030, and then I subtracted 2X, which is 0.06, and it left me with 0.04, but I also have to put a concentration for the Cn minus over here. So this is my new initial. This was a final for the top, but now it's my new initial. I'll start my second ice table. I'll have a change line in here and an equilibrium down here. So now I can fill in my numbers. This will be plus X here, this will be plus 2X, and this will be minus X. And just for form, right, you notice these are minus here, plus here. Now it goes in reverse. So what this represents is the moving towards the right, towards the products, and we went all the way past, and now we're coming back to the left, and that's what the negative designates over here, and I'm forming more reactants again. So this will be X, and then 0.04 plus 2X, and this is 0.030 minus X. And then I can write Kf. I know from looking at the equilibrium reaction, I have silver ion up here, right, silver cyanide, and it's a concentration, so technically you put brackets around it again, which makes me crazy, but it is what it is. And then on the bottom I have Ag plus, and then I have Cn minus squared. And then I can plug all these expressions in, and I'll be able to do my calculations from there. So, what can I assume, right? Yeah, so it's done. Oops, that's what we get. Okay. Why did it disappear? I'm not exactly sure. Oh yeah, I originally did this on 2 slides. So this is your equilibrium constant, and now you can solve it for X. And the assumption that you're going to make, again, is X is small, okay? This equilibrium constant says the product should be way to the right, and so it's not going to shift very far left. That is, X is going to be small going back to the left, just because the equilibrium constant is so large. So we get to write then that 0.030 divided by X times 0.04 squared is equal to 1 times 10 to the 20th, and then we can rearrange this so that X is equal to 0.030 divided by 0.04 squared times 1 times 10 to the 20th, and for sure that will make that value small if nothing else does, right? And X ends up being 1.875 times 10 to the minus 19. So if you want to know the concentrations of the ions in solution, you take X and you plug it back in here, and you got to do this one as well. Well, since this is such a small number, right, the molarity of silver cyanide for all practical purposes is 0.030. The cyanide ion concentration is going to be 0.04, and then the silver ion concentration will be this 1.875 times 10 to the minus 19. Okay, so if you remember when we first started talking about solubility and the common ion effect, I said there's kind of two effects. One is if there's a common ion present, right? And that if the common ion is present, we sort of decided at that point, right, it always lowers the solubility because not as much of the solid can dissolve. But now we're going to look at a different situation. Again, this is another coupled equilibria. And now we have the formation of a complex ion, which is pulling the metal ion out of solution. Okay, so we have a KSP equation where we have a metal salt here that's dissolving into solution, and I have a KSP that's, generally they're pretty small. But then at the same time, I have a coupled reaction, right? And it's competing for the metal ion in forming the complex ion. And remember, these things have pretty big KFs. So the question is, right, can the KF outcompete the KSP? And if it does, then this metal salt will dissolve. And if it can't, well, the solubility will be higher because you're pulling metal ion out. But for the most part, most of the metal salt will remain. Okay, so with that in mind, there's really kind of two questions I get asked, and we're going to have two sort of unique ways to answer these questions. The first one is, does a precipitate form if I have a complex ion forming a ligand, right? A ligand for a complex ion in solution. The second one is, what is the molar solubility if I have a complex ion? Like, how much can I dissolve if the complex ion, right, is forming? And so again, these are two separate kinds of questions, and we'll cover each one separately. The first one is calculating a Q. The second one is calculating a new equilibrium constant by combining these two to get a new reaction. For this particular situation, when I add them together, right, I'm going to have Mx on one side, which is a solid. And then you'll notice that these will cancel out, so I'll have plus the ligand. Oh, and this should be a plus, actually. And then the equilibrium is going to be Ml plus X minus. And it's kind of a displacement type reaction where the ligand displaces the anion for the precipitation out. And this will be bigger than 1 if Kf has more influence, and it'll be less than 1 if KSP has more influence. And the way that we tell which one's bigger, well, you can just look at them. But to calculate solubility, you would say K net is going to be Kf times KSP. Okay? So the first one's a Q calculation, and the second one is going to be using this sort of net reaction for the sort of the coupling of the KSP and the KF reactions. So here's the problem that we'll be working on. It says predict whether cadmium oxalate will precipitate from a solution that is 0.0020 molar in cadmium nitrate, 0.010 molar cadmium oxalate, and 0.1 molar NH3. All right, so let's break this down and try to identify the different parts of the problem, and then we'll work them out on the next slide. So the first thing is, what the heck are the reactions, right? There's so many things in here. So first of all, take a deep breath. Second is, look at your precipitate. Okay, that's telling you what some of the reactants are for, or some of the reagents in the problem are for. So for example, I'm going to say CD, C2O4, right? That's my precipitate. It will form cadmium ions like this and oxalate ions, C2O4 2 minus. So that's what this is for, the oxalate. And this is actually looking like it's my cadmium, right? So now here's the deal. What's this for? And when you read that, you should start spotting these things. This is a complexing agent. So it's a ligand that's going to form a complex ion. So what's going to happen is the way we treat this problem is we're going to have to say, well, now I have cadmium, and then I have ammonia, and they're going to form a complex ion, which is going to be CdNH3, and then I realize, oh, I'm stuck. I don't know what the reaction is, right? So how do you know what it is? Well, you look it up. So I looked it up, and it has 4 ammonias for every cadmium ion. Now, I'll be honest with you, that one's not in your book. But I've used this example for a few years and was too lazy to redo all the work, I suppose, because it's in my other typewritten notes as well. So now I have the formula for the Kf, and the charge is 2 plus because ammonia is neutral, and my Kf value is 1 times 10 to the 7. So this is what you have to do in this problem. Because you're asked whether or not something will precipitate, you have to calculate Q. So Q is the concentration of cadmium times the concentration of oxalate. And this is actually known as the free cadmium concentration. How much is left after the complex ion is formed? So I have 0.002, so let's do 2.0 times 10 to the minus third. And for my ammonia concentration, I have 0.10, and then I have 0 of this. And I actually have to set up a double ice table to solve this problem. So what I'll end up doing, this is my initial, right? This is my change. This is minus x, and this is x minus 4x, sorry. And this is x. So when I do the calculation, well, if you look, this is 2 times the 10 to the minus third. So I think pretty clearly that'll be 0, right? And then the concentration of ammonia that's left is going to be 0.092. And then this will be 0.002, so 2.0 times 10 to the minus third. Like that. And this is the beginning of your ice table. There's a change. Oh gosh, I'm too far down on the bottom of the screen and it won't let me write. All the commands keep coming up. So this will be plus x. Oh, there we go. And then this will be plus 4x, and this will be plus x like this, minus x. And then Kf is equal to x, or 2.0 times 10 to the minus third minus x, divided by x, and 0.092 plus 4x. And this is to the fourth, and that equals 1.0 times 10 to the 7. So we're going to start by making the assumption that x is small, and I'll rearrange the equation and show you the solved form of it. And so I did the calculation. I just rearranged it. I didn't figure you want to see me rewrite all that at the bottom. 2.0 times 10 to the minus third divided by 0.092 to the fourth divided by 1 times 10 to the 7. You get 2.79 times 10 to the minus 6. So that is your free cadmium concentration. And then you're going to plug in for your oxalate concentration 0.010. So this is 0.010. And we can calculate Q as 2.79 times 10 to the minus 8. Again, I use this concentration in here. All right, now KSP is actually 1.58 times 10 to the minus 8. So this one's pretty close, right? But Q technically is still bigger than KSP, so you expect a little bit of cadmium oxalate to precipitate from the solution. Of course, now that I finished writing all that, I realized, I was really going to write that on the next slide. I had it all set up. Apologize. So got it all crammed in that little tiny space. So the next kind of problem, just getting past that, is that we're going to calculate the molar solubility in the presence of a complex ion. And in order to do that, what you do is you have your two reactions, and you're assuming that they're coupled together, and we get a new net equilibrium constant for the two put together. So, remembering I have another slide. Sorry. I'm going to take my silver bromide. Well, let me read through the problem. So it says calculate the molar solubility of silver bromide in 1 molar ammonia at 25 degrees Celsius. Okay, and then it gives you a KF and a KSP. And so what we'll do is we'll write our KSP reaction like this. And then we'll also write our complex ion formation, which is going to be silver ion plus 2 ammonias. And again, I only get that because I looked it up, right? I don't know how many times I can say that. I know someone's going to ask me, how did you get that? It's okay. We all go through that phase. AgNH3 2 plus, like that, and that's my KSP and my KF. When I add those two together, the silver ions will disappear. That's how they're coupled together. So I have AgBr plus 2NH3 in equilibrium with my complex ion plus Br minus, and my K, my net, right, is KSP times KF. When I looked these up, KSP was 5.35 times 10 to the minus 13. And KF was 1.7 times 10 to the 7. And I didn't check to see if it stayed the same in this edition of the book or not, but those are the values when I looked up and made this slide, actually. Okay, so I start a new ice table, goes like this, right? And we're going to say this is my initial, this is my change, this is equilibrium. I guess I didn't need to make the line quite that long. A little exaggerate-y there. Again, this is the solid, it goes away. And then we're going to assume that this is 1 molar, right? Sorry, we're going to assume it's down here is 1 molar. And I'll talk about that in a second. And then this is initially 0, and this is initially 0. So this is going to be plus S, because we're doing a molar solubility, plus S, like that. And then this is just going to be S and S. So now I have K net. I write the expression for it. It's going to be the concentration of the complex ion, which I'm tired of writing, but I'll go ahead and write it one more time. And double brackets because it's a concentration, Br minus, divided by the concentration NH3 squared. And that's going to be equal to my net equilibrium constant, which is going to be, when you multiply this together, it's 9.095 times 10 to the minus 6. So that's what I have down here. And then I can just plug in. This is going to be S squared over 1 squared, actually. And so S ends up being, plugging in S and S, and then 1.0 for this one. S ends up being 3.0 times 10 to the minus 3rd molar. So in the presence of 1 molar ammonia, silver bromide, right, has a solubility of 3 times 10 to the minus 3 molarity. Okay. All right. So sorry. I hope that wasn't too confusing because I did forget to actually use some slides, and yeah, just crammed a bunch of junk together. So I apologize. But hopefully you understood what I was doing there, and if not, you can always ask me questions.